Hello, this paper presents load carrying capability of renewable energy sources of Bangladesh power system. The authors of this paper are Mohammed Karam Moni Rabi, Nahid Al-Masood, Mohammed Mobaidul Islam, and Nabil Kauza Genie. This research was conducted in the Department of Electrical and Electronic Engineering at Bangladesh University of Engineering and Technology, Bangladesh. I will walk you through the structure of our presentation. We'll begin with a discussion of the problem and a brief literature review, followed by our modeling approach. Then, I'll explain the theoretical analysis, present the results, and finally, discuss conclusions and future work. Our work builds on several key studies in the field. Gova introduced the concept of effective load carrying capability in 1966. Milligan and Porter surveyed methods for valuing wind capacity. The North American Electric Reliability Corporation addressed high variable generation integration. Wang Di et al. Explored factors affecting ELCC for intermittent sources, and Billington and Fotuhi Firuzabad studied reserve capacity in isolated systems. Continuing the literature review, Billington and Bai studied capacity adequacy with wind energy. Billington and Allen's textbook is a foundational resource. D.A. Silver et al. Worked on probabilistic evaluation of reserves with renewables. Billington and colleagues also developed frameworks for system health and well-being analysis, which are relevant to our reliability assessment. Further foundational work includes Billington and Karki's application of well-being analysis, Bagan's doctoral thesis on wind and solar reliability evaluation, Billington and Lian's work on composite system health analysis, and D.A. Silver et al.'s well-being analysis for composite systems. These studies inform our methodology for assessing PV integration. We model each generator as a two-state system, available, with probability P, or on forced outage, with probability Q, the 4. The formulas shown relate these probabilities to mean uptime and downtime. The Bangladesh power system has 86 generators with a total installed capacity of 6,545 megawatts. Their individual capacities and force were used in our analysis. To model the system load, we used hourly load data from the National Load Dispatch Center of Bangladesh for 2012. The probability of a load level occurring is calculated as the number of days it occurred divided by the total days in the year. This probabilistic load model is essential for calculating the loss of load probability. PV generation is intermittent and depends on sunlight. We modeled PV availability based on average daily sun hours. Assuming 8 effective sun hours per day, the availability, P, is 8/24 or 0.333, and the unavailability or for IQ, is 0.667. This model treats the PV plant as a generator with this specific 4, reflecting its weather-dependent nature. To handle the enormous number of possible system states, 2 to the power of 86, we used a recursive algorithm to build the capacity outage probability table, COPT. The formula updates the probability of a system outage state, XMW, after adding a generator of capacity C with a forced outage rate U. This method efficiently combines generator outage distributions. This slide illustrates the recursive algorithm step by step for a small 3-generator system. Tables show how the state probabilities are calculated as each unit is added. States with identical outage capacities are merged, which drastically reduces the computational burden for a large system like BPS. After computing individual state probabilities, we arrange outage states in ascending order and calculate cumulative probabilities. The cumulative probability for a state is the sum of probabilities for all states with outages greater than or equal to that state's outage level. This is a key input for the LOLP calculation. The loss of load probability, LOLP, for a specific load level is the probability that the system outage capacity exceeds the available reserve, installed capacity minus load. The total system LOLP is the sum, over all load levels, of each load's LOLP weighted by its probability of occurrence. The load carrying capability, LCC, of an added generator is calculated using linear interpolation on the new system's COPT. We find the new available capacity that yields the same LOLP as the original system. LCC is the difference between this new available capacity and the original system's available capacity. The percentage loading shows the effective utilization of the added generator. Our key results are summarized in this table. We analyzed the addition of a 500 megawatts PV plant with different forced outage rates. As you can see, with a low FOR of 0.1, the LCC is 486 megawatts, 97% of its capacity. As the FOR increases to 0.667, typical for PV, the LCC drops to 294 megawatts, or about 59% loading. This quantifies the reliability impact of PV intermittency. This graph visually demonstrates the inverse relationship between FOR and LCC. As the forced outage rate, representing unavailability, increases, the effective load carrying capability of the added PV generator decreases significantly. This highlights the importance of reliability modeling in planning. This companion graph shows the same relationship in terms of the percentage loading of the added 500 megawatts generator. It clearly illustrates that a highly reliable generator, low FOR, can be loaded close to its nameplate capacity from a system reliability perspective, while an intermittent source like PV provides a lower effective capacity contribution. In conclusion, the LCC method is a powerful tool for assessing the real capacity value of intermittent generators like PV. It provides system engineers with a reliability-based metric for planning. For future work, this PV reliability model could be extended to dynamic or transient stability studies, and LCC could be investigated in the context of voltage instability to ensure reliable operation. The development of load-carrying capability of renewable energy sources of Bangladesh power system is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.